lesson. So if I give the heading rate equation, offer you how to draw a Maxwell-Boltzmann distribution plot at two different temperatures, and also with and without a catalyst, because what you drew there was pretty ropey. And I'm not going to spend loads of time on this. I'm going to put number of particles here, and I'm going to put energy here, or kinetic energy across here. And you did this pretty well. So your distribution of this was pretty good. You seem to have the idea very clearly that the energy at a given temperature is distributed over that kind of arrangement. So no particles have no kinetic energy. A tiny number have infinite kinetic energy. This line does not touch the horizontal axis. We've got to leave it like so. And we've got number of particles. You might have been told frequency up there. It's all the same, but that's the distribution. And the area under that that distribution plot relates to the number of particles, right? And what you told me so far, you sort of understand that really well. But you can mark on there the activation energy, which is the minimum energy required for a reaction to take place, and you all draw an activation energy on there, which is pretty good. And hopefully you can define that, because you are expected to know a definition for that, which I've just said, but I'm not going to repeat that now either. Now it's this proportion of the total number of particles. So that area of the graph, the proportion that's shaded there, is the proportion that have energy greater than or equal to the activation energy. In other words, the collisions between the particles are going to have sufficient energy to cause a reaction, or going to have enough energy to be successful. Now, if you were to do that at a higher temperature, that curve changes, but the activation energy doesn't change. And the area under the curve can't change because the number of particles can't change. And so I tend to get students to think of this line like a piece of string, and imagine sort of tugging on this piece of string here to pull the whole curve to the right to show that the particles have more energy. So make my peak there, let's say. I worded that particularly well. Nor have I drawn it that well, but that curve gets pulled to the right, and again can't touch the horizontal axis. But you get a mark for recognising that peak is shifted to the right, but you also have to recognise that it comes down a little bit, and also that the proportion of particles that have E greater than EA, in other words, the proportion of the curve that's shaded now has increased. We've got to be a bit tighter on that than you are, and I'll ask you that again either later in the lesson or at the start of the next one. Some of you on your curves drew the effect of adding a catalyst, which I'm not going to spend long on today either. But if that's your activation energy for a normal reaction without a catalyst, and you keep the temperature the same but add a catalyst, we call that EA cat, then the proportion of particles that have energy greater than the activation energy increases as well. So that stuff you know but aren't secure on, I would say, and that needs to be really, really tight as we move on to orders of reaction. Okay. So we'll come back to that. We'll practice it, but don't let it slide just because it's been a while since you've done it. Right. Okay. So we're just going to assume now that sort of we're starting from the beginning, but you've been told for a long time that basically if you increase the concentration of a reactant, then the rate increases, and we're just going to talk about why for a second. So kind of GCSE version or standard level version as well is you increase the concentration, you increase number of particles per unit volume, and we increase the frequency of collisions, right? That's all perfectly reasonable and makes perfect sense, right? However, it's not always true, because that's what we do. Sixth form chemistry tell you everything you've been told before isn't quite true. It's not always true, and it's certainly not detailed enough. So in most cases, it's fair to say, you do get that going on, and you do get a directly proportional relationship. So if you double the concentration of something, you double the rate. So let's say in most cases, if the concentration doubles, then the rate doubles. And we say that that is, of course, then directly proportional. And you're just going to convince me now that you're happy with the meaning of directly proportional and how you'd spot a graph that's directly proportional. And we should all know then, shouldn't we, as you've convinced me from the discussions you were having, directly proportional relationship is like that. It goes through the origin. As one increases, the other increases, and it does so linearly, something like that. Okay, so as concentration increases, rate increases. And so what we can say in that situation is the rate is proportional to the concentration. And what I'm going to do, I'm going to call it this reaction, A plus B goes to C. And so we're going to say rate is proportional to the concentration of A. Okay. And give me a chance to catch up. We can say, in this situation, we can say that this is what we call a first order reaction with respect to the reactant A. And that's because if I were to put a power on that concentration, that power would be 1. We don't normally bother writing things to the power of 1, do we? Because anything to the power of 1 is just itself. So 6 to the power of 1 is 6, and 24 to the power of 1 is 24. But if we've got a directly proportional relationship, we say that the following. So in this reaction, and in most cases, in fact, so the order with respect to the reactant in that equation there, with respect to A, is 1, or we say it's first order. And that is to say, the concentration is in the rate equation is raised, the concentration is raised to the power of 1. Well, that's your standard reaction, the kind of thing you're talking about at GCSE and so on. But there are a couple of situations where that doesn't happen, and we're going to talk about those in a sec. So sometimes the order of reaction with respect to, I'm just going to use WRT as with respect to from now on, with respect to a reactant is 2. In other words, it's what we call second order. And we'll explore next week sometime what that kind of means in terms of how the reaction works. But for now, we're just going to consider what the relationship is. And if you've got the concentration of A there and rate there, you'd have the kind of graph that you were just sketching on your mini whiteboards, so something like that. And so we can say that rate is proportional to A to the power of 2. Okay, and that's all I'm going to say about it for now, except one little detail, which I'll definitely come back to, is that if you were to draw, a little challenge for you, if you were to draw, and the IB quite likes this, if you were to draw a graph between the concentration squared and rate, what would that look like? What do you think? If the rate is proportional to A squared, rate A squared, just a proportional relationship. So some of you picked that up very quickly, some of you fell in the trap that the IB like to set. It's just that relationship. Of course, rate's proportional to a squared. Rate proportional to a squared. So watch out for that one. But we'll come back to what that means and where it comes from in due course. But what we're going to do now is we're going to look at the third scenario, which is sometimes changing concentration of a reactant has no effect on rate. And this is really surprising and completely non-intuitive. So I take a reaction between A and B, shove in a load more B, make it more concentrated, and nothing happens to the rate. It doesn't change. I think that's really non-intuitive. And we'll have to think about, from a chemistry point of view, why that's happening next week. But it's definitely not obvious. Has no effect on rate. And as we say there, the order of reaction equals 0 with respect to a particular reactant. And so what you'd say is that, well, sometimes it's written as 0 order with respect to whichever. And so a good example would be rate is proportional to B to the power of 0. You should know, shouldn't you, that if you raise something to the power of 0 from your maths, what does that mean it is? So 24 to the power of 0 is what? What, 163 to the power of 1 to the power of 0 is? Right. So that means this, all we're looking at, we're not going to put any numbers on this, but we say that the rate is unaffected. So whatever the rate is, it's unaffected by the concentration of B in our reaction. A plus B goes to C. So we say 0 order with respect to B there. So that's the relationship there. We've got to know those three graphs, and they come up really quite a lot. Okay, so we're going to be comfortable with all three of those. We've done that. Right, so we're going to then see how these get brought together in the rate equation. And that's what this next little section is going to be. So the rate equation. So the rate equation shows the order of reaction with respect to each of the reactants, including catalysts, in one equation. So if we just bring it all together into one equation. And so if we've got a reaction, let's say A plus B, and we'll say that C might be catalyst, for example, makes D. That could be our reaction. If I just put C as a catalyst. So we can write a rate equation for that reaction, and we'll talk in due course about how we work out what the rate equation is experimentally. But the rate equation will look something like this. So rate is equal to K times A to the power of 0, let's say, B to the power of 2, and let's say the catalyst to the power of 1, just for argument's sake. Okay. And so we can work out what the rate equation is experimentally. So rate is proportional to A to the power 0, rate is proportional to B squared, and rate is proportional to the concentration of C. And I just want to check that you're comfortable with this maths. I'm not going to talk you through it, but you're comfortable with this kind of maths. If I say y is proportional to x, we can say that y is equal to some constant times x. I'm going to call the constant p for whatever reason. You're happy, you've seen that sort of stuff before, right? So that's what I'm doing here. So this here is what we call the rate constant, which is, we'll learn in a few lessons time, probably in a couple of weeks, and we'll learn that this is dependent on a bunch of things, but it's dependent on activation energy and temperature, and we'll see it's a fairly complex thing we'll look at called, I'll forget that, we'll do that when we get there. So in this situation, the order of reaction with respect to A equals 0, B equals 2, and C equals 1, right? That's dead easy, isn't it? But we need to say that the overall order is equal to 0 plus 2 plus 1 is equal to 3. So it's an overall third order chemical reaction, right? And even though it's squeezed into the bottom of the page here, this is a really important point I'll make, and we'll make multiple times when we're going through this, is orders of reaction can only be determined can be found out experimentally and you'll do those experiments. You'll find out that if you double the concentration of something, the rate doubles, or if you double the rate of something, nothing happens to the rate, or if you double the concentration of something, the rate quadruples. And those sorts of experiments will allow you to determine the order of reaction of things. And we'll do that all in due course. But one thing we must make a note of now is ignore the coefficients in balanced equation. They have nothing to do with the order of reaction. That's just the molar ratios. It's got nothing to do with rate of reaction. Don't forget that. Okay, so that's that done. I think what we need to do is a little bit of the bookwork now. I'll have a little pause from this for a second. All I'm going to do is just to point out to you that when I asked you a few things about Maxwell-Boltzmann distributions earlier in the lesson, you weren't super secure, and it's all here. So I'd strongly encourage you to take responsibility for kind of re-practicing that and learning it. Right, that's what it should look like, and that's the effect of changing temperature on the Maxwell-Boltzmann curve and how it looks, and the effect of all of the different factors which affect rate is all explained there, and that will do nicely. So that's what you've got to learn. Make your flashcards on it, those of you who were slipping up on that earlier on, and be really comfortable with it. I'm not going to get you to do this right now. We'll come back to this a bit later on, so don't worry about this page for now, or this page for now. But we will at some point come back to this. We'll make sure that we're comfortable with the idea of finding rates. It's something you did when you did the standard level version of this topic anyway, isn't it? But we'll so drawing tangents and so on. But I do want to come back to it later on. But what we're going to do is to move on to page 6, which is looking at the rate equation and orders. Now, everything I've just taught you, you could argue it's a complete waste of time because it's all in here anyway, right? So you've got a backup of information here, but we're going to learn how to work out the order from data in a second. So everything that's here is basically what I've just said, but let's look at how it's set out here. So just eyes up top here, please. So if you've got a reaction which is zero order, and if you consider, we're just considering it with respect to the concentration of A, basically it doesn't matter what you do to the concentration of A, the rate will be unchanged if it's zero order. If it's first order, you double the concentration, you double the rate, you times the concentration by 10, the rate times by 10. Simples. The one that people struggle with a bit more is the fact that if it's second order, it means you've got to work out by squaring the changing concentration to get the new rate. So the concentration is doubled, the rate is times by 4. The concentration is changed by 3-fold, so it's changed by 3 squared, which is 9, the rate, that is. If you halve the concentration, the rate would be a half squared, which is a quarter, right? So, and that's all the stuff I've just said. So it's all sort of backed up there. What you're going to do is start to look at this, and we'll do a few together, and then I'm going to let you get on with it yourselves for a little while. Okay? So, again, just have eyes up here if you can for a minute, please, so you're with me. Now, the first thing I point out is the reaction here is irrelevant what the reaction is in a way. The coefficient makes no difference, even though these are all 1 to 1 to 1. Changing the product is very rarely going to have any effect on rate. There is a rare situation of something called autocatalysis, where one of the products can catalyze the reaction, but that's pretty rare. So we can ignore the change of concentration of D. But the order of reaction with respect to A is 0. What's the order with respect to B, everybody? Show me with fingers, please. What's the order with respect to B? And what's the order with respect to C, please, everybody? Show me with fingers. Yeah, good. Right, so let's say we've got an initial rate of 0.75, and then we times the concentration by 4. So what's the effect of the rate going to be? Well, it's first order, so it's going to be times by 4. So we take the rate and we times it by 4. 0.75 times 4 is 3.0. Simples. It's second order with respect to C. If the initial rate is 12 and the concentration's increased by 10 times, we've got to do times 10 squared, times 10 squared, which is equal to times 100. So we've got to do 12 times 100, which is 1200, right? So whatever's happened to the concentration, we've got to square it. Let's do one more of those. We're going to do this row here, 3.5. Can you just tell each other now what the effect is going to be on the rate of dividing the concentration of C by 3? Discuss that now. Simply, I had all sorts of things, but simply divided by 9. So divided by 3 squared. So you do 3.5 divided by 9, which is 0.38. So you are going to need your calculators here. Changing D is not going to have any effect, so we're going to ignore the ones with D in. And apart from that, it's relatively straightforward until you get down here somewhere where you're maybe changing B and C. So let's just look at this row, then I'll shut up. Right? So the effect of changing the concentration by threefold, what's that going to do to the rate? Just that first bit, please. What's that going to do? Never mind, 3.6. I forgot the decimal point when I was doing it, and I was out as well. But can you do the rest of those rows, and then as soon as you're done, you can move on to that side, please. Have fun. Now, so what I want to do, just briefly with you, if you could just stop with the sums for a bit, we're going to just talk about the rate equation a tiny bit more. Now, so you've seen that the rate equation is something like, so this little subheading now is going to be units for rate constant K, and this depends, and I'm going to look at this again with you. I imagine I'll do this again in the next lesson, just to remind you that it's dependent on the rate equation. The units are not always the same. It depends, it's dependent, isn't it? You spell it, on the rate equation. Right, so an important idea. So for example, if the rate is equal, the rate constant is equal, if rate is equal to the rate constant times the concentration of A, then in order to work out a value for K, which we'll learn to do in another lesson, and the units for K, what you need to do is to rearrange the equation to make K the subject of the equation, and you're all capable of that. So I'm just going to do it for you. So rate divided by the concentration of A, right? That's easy enough to do. So what are the units for K? Well, you can work them out depending on the units for rate and concentration. But the units for rate are always going to be the same. So they're moles per decimeter cubed per second. That's always going to be the same, and you need to be confident and comfortable with that. And the units for concentration are always going to be moles per decimeter cubed. And so to work out the units for K, all we've got to do is cancel out. Just put your pens down for a second. Let me just walk you through a couple of these, then you can write up. Right? So moles per decimeter cubed appears on the bottom and the top, so it just cancels out. So we can say the units for K for this reaction here, this overall first order reaction, are simply seconds to the -1. I'm going to do one more example with you, then you can get on, and those of you who finished task 2 can move on then to task 3, which asks you about this. But this is always the case for overall first order. But rather than just memorise them, learning how to do them in an exam is really good. But we'll do a second example. We'll do rate is equal to a concentration of A squared. So it's an overall second order reaction this time. To rearrange it very simply, rate is over concentration of A squared. Units for rate, same as before, moles per decimeter cubed per second. And the units for concentration now, if there are two things, this could be A, this is the same as writing A times A, isn't it? Or concentration of A times concentration of A. So we have to have the units for A and the units for A again. You can either write moles per decimeter cubed squared, or you can write it out twice. You have to see what's going on here. For at least the first time you do this, I like to write it out twice. And if it's a fourth order reaction, you need to write it out 4 times. But you can only cancel out one of those. So moles per decimeter cubed cancels once at the top and the bottom, leaving you with seconds to the -1 over moles per decimeter cubed. If you want to write that order as units, what you would write is seconds to the -1, that's not changed, but you want to get the moles and decimeter cubed back on the top. So 1 over mole is the same as writing mole to the -1. dm to the -3 up top, or 1 over dm to the -3 is the same as writing dm to the 3. And the seconds to the -1 don't change. So the units for K there are moles to the -1, dm's cubed, seconds to the -1. Really unusual looking units. And you can do exactly that approach for the other ones on task 3 if you're rattling along and you finished task 2 already. So that is all I'm going to say on this. I'll come and give you a hand as and when you're stuck. On you go.